here.
You want to go there?
This place, yeah.
Go on, let's see.
Do we need to?
Okay,
Okay, let's start the last session for today. We have 3 more speakers. The first one is Dr. Marcus Gellert from Potsdam.
Potsdam Astrophysical Institute. Yes.
So I'll warn you 5 minutes.
Okay, thank you, Alfie. Yeah, we continue with the cylindrical geometry. I want to talk about helicity generation and alpha effect in MHD tailored grid flows. Start with a motivation. So, on one hand, we have the laboratory experiments, which have really nice time scales, and we can change everything. But of course, the idea behind is to figure out what is really important for the astrophysical bodies, or the inside of stars, for instance. And there we have several ingredients: differential rotation, we have these magnetic fields, magnetic instabilities, and I want to talk about magnetic instability, the Taylor instability, or current-driven instability in a cylindrical gap flow. I start with this astrophysical motivation, show you a model where I study the instability of a given toroidal field, and in a second step make it more dynamically, where I start with a toroidal field, which is wind up in strong differential rotation. And then I will come to the last point, if it might be possible to get a dynamo just based on this magnetic instability and differential rotation. Can you measure it with the Werner and alpha effect? So we already know that if you look at measurements for white dwarfs, which are shown here, over the mass and the angular momentum of these white dwarfs, which are remnants of sun-like stars, and after the lifetime they lose their envelope, and we have just these white dwarfs, these cores, and measure the rotation rate. And from observations, one finds a line, that's the dashed line here, which is the upper limit of the rotation or of the angular momentum. And for the development of models for such stars, one starts at a very strong rotating star, which columns and rotates. That's the green line here. So we focus on these small or sun-like stars here. And if we do not include, or we would not include any magnetic fields, so the white dwarfs we get after the lifetime of such a star would be rotate much too fast and is not in agreement with the observations. But if magnetic fields, or in these calculations, especially the action of a magnetic instability and the enhancement of angular momentum transport is included, that's the red line here, one is in good agreement with the measurements, at least with the upper limit. So this says us that magnetic instabilities are for the development of the stars, of coupling between cores and envelope, might be really important. And one possibility would be the Taylor instability, maybe also the magnetic rotational instability of several flavors are interesting. There are also kind of stars, the so-called AP stars, where one can observe the magnetic fields and find a pattern which is really dominated by m=1. And it gives also the hint that maybe there, below the surface, the magnetic instability or Taylor instability, it's also working there. So that's the motivation from an astrophysical point of view, that these several kinds of non-axisymmetric instabilities, especially the Taylor instability, might be really important. There's another simulation, so that's the dotted line here from Eggenberger, that's the rotation rate of a sun-like star, and these arrow bars and dots here are measurements, and only if you include the magnetic fields, here we are in agreement with the measurement. Without magnetic fields, it would be rotate much too fast. So that's the method we have from these observations, and that means we have to figure out what really are the boundary conditions when the Taylor instability appears, how strong is the angular momentum transport, and another step then might bear the possibility to have a dynamo based on this instability, which means you wind up a strong toroidal field, which is axisymmetric in a strong shear flow. It becomes unstable, evolves non-axisymmetric parts, and if then there is somehow a mechanism, let's call it alpha effect or whatever, which from these non-axisymmetric parts produces again a small poloidal field, which can be then again add due to the shear to the original toroidal field. Maybe there would be the possibility of a dynamo just based on these magnetic instabilities. Okay, just for the information, they're missing arrows. So there are several flavors of MRI. The helical MRI, the promise experiment, Frank was already mentioned, and now we concentrate on this third case here, a pure toroidal field, where the ultimate magnetorotational instability is driven by the shear flow and the current through the inner cylinder, and the Taylor instability by a current directly through the fluid. So that's the setup. The Vegas ratio here for our cylindrical setup is 0.5. If there is rotation, then it's quasi-Keplerian, and I apply perfect conducting boundaries of zero vacuum. And the two cases I already mentioned, first starting with a fixed toroidal field and starting this instability, and the second I start with a fixed radial field. Look if it's possible to get a strong toroidal field to become unstable. Magnetic frontal numbers are around 1, change it means 10 and 10 to the minus 2. Magnetic Reynolds number is defined on the rotation of the inner cylinder, the same for the Hartmann number. And the most unstable mode in that case, it's the M equal 1 mode. We've seen one example here. You can see there are both the M equal plus 1 and M equal minus modes having a different handedness. The applied field has a radial shape. It is given by this number μb, which in that case we are talking here about is nearly a constant field. Additionally to this predefined toroidal field, here I add a small axial field also, and the parameter beta here gives the ratio between the applied axial field to the toroidal field. So that means pure toroidal field for beta equal infinity. As I said, M equal 1, it's the most unstable mode for all the setups here. The critical Hartmann number, it's not depending on the magnetic frontal number, which is nice if you think about laboratory experiments. And the questions I want to ask here is the production of helicity due to the instability and the strength of the radial or poloidal field we get out of the instability. First, let's start with the non-rotating case without any axial field applied. So there's no predefined direction. The system is completely free, and what we see, depending on the initial conditions, are either an M equal plus 1 or an M equal minus 1 mode. So there's a spontaneous symmetry breaking depending on the initial conditions. In the beginning of the setup, you will see that both modes are somehow excited, but at the end, at the stable state, only one mode survives, and you get either the plus or the minus 1 mode. So the following, the kinetic helicity and current helicity are based on the definition that fluctuations are defined as non-axisymmetric modes. So averaging is only along the azimuthal direction. And we have here figured out two cases, which means the one where we have a fast rotation Reynolds number larger than the Hartmann number, and a slow rotating case, which show a slightly different. So for the fast rotating case, beta here again the measure for the measure for the size of the applied additional axial field. For the fast rotating case, we have a helicity which vanishes for strong beta or beta equal infinity, so without any axial field, and it has a maximum for beta around 3 or 2, and of course it has to be again 0 because then it's unstable, not unstable for beta equals 0. For the slow,
What is beta?
beta is the ratio between the toroidal to the axial field. This ratio. So that means a pure toroidal field here has a very small helicity compared with the case where you have an axial field added additionally. And for the slow rotating case, we see that even beta is infinity, so for this pure toroidal field, the helicity is not 0. But again, we find that there is a possibility for both solutions, m equal 1 and m equal minus 1. So over the average, it should be also 0. So there's always these two branches for solutions for beta plus and beta minus 1. That's the same here for the fast rotation, but plotted only the one side. Nevertheless, so the beta here really defines the sign of the helicity. So the applied background field, the helicity of the background field, defines also the sign of the helicity we get out of the instability. So the only exception is the non-rotating case without any axial field. And the second question is, how strong would be the poloidal field we get out of the instability? And this is several ones for different Reynolds numbers, small Reynolds numbers, several quantity numbers. And first point I want to show here is that the instability is the strongest for PM equal 1. So PM equal 1 seems to be always a somehow exceptional situation. Also, larger magnetic quantum numbers have a smaller instability in the sense that the maximum radial field is less than for the PM equal 1 case. And the limit here seems to be around 12%. And that would be the input for the new generation of the toroidal field. So what would happen if we really do this? We start with a fixed poloidal field proportional to 1 over r. We evolve a strong toroidal field. The shape is shown here. It would usually be of the shape of 1 over r to the third with the differential rotation applied in radial direction, and due to the boundary condition it becomes 0 also on the inner cylinder. And that's what we need for the instability to appear, because we have here the instability condition which says that a field which is constant or it's increasing in radial direction becomes unstable. That's what we can see also here. During the growth, we see that the instability here starts to evolve near the inner cylinder. The original field is nearly Z independent on the outer cylinder. So we have the instability starting at near the inner cylinder, where we have the steepest profile and the instability evolves fastest. Okay, one problem that appears, from my point of view, appears then if we really start with a Z independent radial field or poloidal field, wind it up into a strong B5 that is still independent on the Z coordinate, then the instability appears and produces a wave number. And if we think about a cascade, then we would get a regenerated radial field which is Z dependent. That again would evolve in toroidal field, but also depends on Z. And if this becomes unstable, the wave number is even higher. So if you look on this picture, it seems, at least in the situations we have shown here for these still fixed small radial field, that we get smaller and smaller structures, and it becomes more and more complicated to get enough energy from the instability back into the axisymmetric mode, which can wind up again this toroidal field. So that at least would make the existence of a dynamo mechanism based on these two ingredients more and more complicated. And if we really express such a dynamo, if it would exist or not, in terms of an alpha effect or an alpha omega dynamo, I call it here current-driven alpha omega dynamo, where we would have two ingredients, the alpha effect and the differential rotation, we would have the following picture. This applies only for the cylinder setup. So we start again with this poloidal field, one up in this toroidal field, we have the instability, and from the non-axisymmetric mode we get some axisymmetric poloidal field, and we want to express this effect here as an alpha effect. Then everybody knows that for such a dynamo, a working condition is that the product of the dynamo numbers C alpha, C omega is of the order of 1 or larger. So with the strength of the alpha effect and the shear, we also define the ratio between the toroidal and the poloidal field. And if we put these together, we get an equation with the C alpha only and the ratio of the poloidal and toroidal field. And from the simulations, but so I have to say that's again for the fixed toroidal field. I haven't done this for the model I've shown in the last term. We have the C alpha, and that nearly fits to a 1 over beta shape. So the C alpha can be expressed in a constant times the ratio between the applied axial field and the toroidal field. And if we combine it, we get an equation where we have a constant and only the ratio between the axial and the radial field component. And this C bar, now we get from our simulations, it's of the order of 10 to the minus 2, a few times 10 to the minus 2. And if you put this into the equation, we see that it would need a C bar of the size of 1. If we agree that usually if you have a dynamo or such situation that the set and the radial field component are of the same size. So at least for the situation in the cylindrical gap flow, the existence of such a dynamo, which sometimes is also called the Taylor-Sprout dynamo, because Sprout was the first one who was mentioning the possibility of such a dynamo, seems to be nearly impossible. At least the effect, the alpha effect, it's really, really small. So that's also the end of my talk. I have shown the Taylor instability. It's current-driven, okay, or the current-driven instability here, I will call Taylor instability. It involves non-axisymmetric modes, but also an axisymmetric mode, which can be wound up again into a toroidal field, which is rather effective, but it seems to be there are 2 points which act against the possibility of a dynamo. There's on one hand the increasing wave number, which makes it more and more complicated to get enough energy into the axisymmetric field, and if we express this generation of the poloidal field in an alpha effect, it seems to be much too small to get it into these Taylor grid flow type setups. Especially, it would be impossible, beside other things, to do it in the laboratory. Thank you.
So we have time for several questions.
The production of higher wave numbers, was that actually the result of the direct simulations? Or
That was a result of the direct simulation. So if I start, I can see that the wave numbers become less and less. The only problem here I have is that I always have the input from the fixed poloidal field. So it also or always regenerates out of these small wave numbers. So I think if one would do that as an initial condition only, it would be even stronger, this effect.
This is called secondary instabilities, right? So the instability produces the solution which is also unstable. It's a secondary instability.
Which instability? We have only the Taylor instability, only one instability involved.
He asked about the high wave numbers. Secondary instability.
Oh, in that sense, okay. Yeah. Could maybe for the secondary instability. But I would more say that somehow a cascade. If the instability produces a wave number, then in the next loop you get an even higher wave number.
You calculated the helicity from the instability. Did you calculate the EMF as well?
I did not calculate it for this setup, but I have done this for a little bit different, but also for this gap flow, and we see that the eddy diffusivity, maybe that's the background of the question, it's always of the order of the molecular diffusivity, 2 or 3 times.
No, I was just wondering if the EMF is related to the helicity, if you calculate both. I'm just wondering.
No, so then I did not.
Yeah, as far as I know, the idea of this dynamo cycle was first proposed by Sproit, and later on, not much later, in fact, Braithwaite claimed to have confirmed it in a sphere with direct numerical simulation. So I know that this claim is maybe... Sorry?
So this proof was in a cylinder.
Oh, you're right, you understand. Yeah, how would you relate your work with Braithwaite's work?
Well, that's really complicated. So there's one thing that's completely different. Braithwaite was using differential rotation d omega over dz, so depending on the z direction. And we tried the same, and also I was discussing with him, and up to now, I would only say nobody else was able to find such a dynamo, even with the same setup.
And another question, but maybe more to Afio, in order not to let us die stupid. If we have the time, could anybody, maybe you, demonstrate the difference between what you call current-driven and what you call Taylor? Because up to now, I believe that Taylor is more broad than the simple kink, and simply incorporating it. Okay.
Yes, okay, maybe I can mention this later, but basically the idea here, the essential point here is that you have BZ. So, and then you have a current along Z. Okay, and that is exactly this type of coupling which induces a new type of instability, which is of a resonant type, and the instability criterion is the sodium criterion, and have been studied by by the people, the group by Ronnie Keppens and the group in Belgium, and then by myself. So one has to look exactly at the restoring force in the case where you have a current along Z and also a BZ component, which is fully different in the case there is no BZ. It's completely different.
That's only one case that you study the influence of an BZ here. The instability is that one of the toroidal field, and as I've shown, the first pattern here, this symmetry breaking, it's just this pure toroidal field which becomes unstable here. So it's.
But you have B5, BZ.
There's no BZ.
No, you have these big
so
beta.
that's the beta equal infinity or without any BZ.
Okay, now I'm talking about the presence of beta, non-zero beta. You show the plot with non-zero beta, no?
That's the study of the helicity, that's the influence of an additional extra field.
And that is why I'm a bit worried about what you talk about Taylor instability, because in general we expect to have a completely different range of spectrum of instabilities which have a different character.
Okay,
That
in
is
our
something,
case,
so
we
I'm wondering
still
whether you're
see
really
that
looking at, you're really seeing that in that simulation. That those are resonant. So only one particular vertical wave number should be you should have in the spectrum. Anyway, I don't want that to become too technical, so we can discuss that later if you want.
Just a question regarding this plot here. Here you see the maximum value. Is that the maximum during the time evolution, or how does it?
That's an averaged volume
But it
average.
does increase and decrease again, right? The helicity, just as a function of time, especially on the beta equals 0 line.
Well, I've only looked for the value after the saturation, so.
But it does increase.
Sure, if you start the
And then it
simulation
decreases
at
again,
0
right? Yes. Okay.
Okay, if there are no other questions, let's thank the speaker again. Now we ask for Dr. gellert+chatterjee from Nordina, I guess.
audible? Yeah, I think so. My ear is good enough. Okay. Yeah. Sorry for the technical glitches. So, I am also going to talk about alpha effect from an instability, in this case magnetic buoyancy instability. So, in order to motivate the problem, I shall start with the classical idea of the solar dynamo, where the toroidal fields are generated at the base of the solar convection zone, where the tachocline is located, and then the small scale helical turbulence twists the rising magnetic, the toroidal flux tubes to form colloidal loops. And this cyclonic this alpha due to the cyclonic turbulence in the solar convection zone is positive in the north and negative in the south, beyond any doubt. But there are few problems. One of them being that this turbulent alpha will be quenched when the toroidal field is very strong. And the next problem is that if you build a dynamo model out of this alpha and omega, the dynamo wave propagation has to obey the Parker-Yoshimura rule, which means that for solar-like rotation profile, which has negative shear in the high latitude tachocline, the dynamo wave will propagate equatorward, whereas in the low latitude tachocline where the shear is positive, the dynamo wave will propagate poleward. So then we will have two branches of the dynamo, which is not quite what we observe in the sun. So thus we need to maybe have some alternate alpha effects from various instabilities. Those instabilities may be hydrodynamic instabilities or it may be hydromagnetic instabilities. So in this case, in this study, I'm going to discuss about an alpha effect which is driven by magnetic buoyancy instability, MBI for short. What happens here is the magnetic buoyancy instability causes vertical motions, and in presence of rotation, this motion can be converted into kinetic helicity, which drives an alpha effect. And it was published in a paper by Schmidt 25 years ago that this alpha effect changes sign somewhere at the mid-latitudes in such a way that the dynamo wave in such a model would always propagate equatorward like we observe in the sun. And also another attractive feature is that this alpha is not quenched by strong toroidal fields, because this alpha is being caused by the strong toroidal fields in the first place. So now so the study of magnetic buoyancy instability has these exactly two attractive features here. But this buoyancy instability has also been studied for various other reasons in the past, and I present some linear stability analysis which have been done by different people. And the first row here, these people have concentrated on smoothly varying magnetic fields, which means that the magnetic fields vary on the scale of the system, and then they lead to the same buoyancy instability, and then we can find out whether we can form magnetic flux tubes out of those instabilities or not. And second, there are these studies about discontinuous horizontal magnetic fields. When I say discontinuous horizontal magnetic fields or smooth, spatially varying horizontal magnetic fields, I am only talking about the initial magnetic field in the system. And in case of this discontinuous initial horizontal magnetic field, we get a Rayleigh-Taylor type of instability, because this magnetic layer will have a lower density than the surrounding atmosphere, and then it will develop kind of density instabilities like you have in the Rayleigh-Taylor case. So Schmidt in this paper, he said that these instabilities would take the form of magnetostrophic waves, which are due to the balance between which are driven due to the balance between the Coriolis force and the Lorentz force, and also an alpha effect, which is generated due to these waves change sign somewhere at the mid latitudes. Later, notice that all these calculations have been done with rather simplified assumptions of anelastic and inviscid, whereas Taylor in 2000 he did an analysis with a fully compressible system, and he solved an eigenvalue problem where he showed that this alpha is actually proportional to the radial gradient of the toroidal field, and if such a thing happens, we can use such an alpha in a mean field model and make make alternative solar dynamo models. And these are subsequent numerical studies. The first two of them are again, they deal with the magnetic fields which vary smoothly, for example, has a linear profile from the top to the bottom of the box. And they all lead to formation of isolated magnetic flux tubes. And some of these studies are compressible, rotating or non-rotating, and some of them are anelastic. And I would point out this study, which is kind of an inspiration for this problem which I am talking today, where they calculated the alpha effect numerically for such a for a box which is stably stratified and has a magnetic layer, has a horizontal magnetic layer in somewhere in the box. So this is what our setup looks like. So there is a box which is placed. This is the box which is placed at the colatitude theta, and the with the rotation axis here. And the dimensions of the box are such that the width and the height are equal, and the length of the box is thrice the height of the box. And there is a magnetic layer which has initial horizontal magnetic field By, and it is placed somewhere not quite at the bottom of the box, but a little higher. And the thickness of that layer is 1/10 the size of the box. And then we do all our simulations with initial velocity field such that the kinetic helicity density, not the kinetic helicity, the total kinetic helicity, but the kinetic helicity density is 0. And we have periodic horizontal boundaries, and we use rather low resolutions of 64 cubed or 128 cubed. So, yeah, we may forgot to mention that we use polytropic density and entropy profiles, which have a polytropic index of m is equal to 3, which means that they are highly stabilized, and we don't want any influence of convection in this problem. So, when we introduce the magnetic layer, we actually disturb the hydrostatic balance of the polytropic layer, and what we do is we make the layer neutrally buoyant, or we don't change the density, but we cool it artificially, so that the layer initially has the same density as the surrounding, but later on we find that the layer develops these finger-like projections which are reminiscent of the relateral instability, and this is actually a contour plot of density through a vertical cut at the middle of the box. So this is x versus z, and I have cut it at y is equal to 0 plane, and this is the contour of density, and you see that these fingers really have low density in it, and hence this is really a buoyancy instability. And this is the same thing, but for the magnetic field By and the current density J dot B. So you would see these, they have developed into these tubular structures here, which have a tilt because of the Coriolis force. This is a familiar thing here, and they develop quite a bit of current helicity density in it. And keeping everything else constant in the box, we vary what we call as the Roberts number, which is the ratio of the temperature conductivity to the magnetic diffusivity, and we get two interesting results, one of which have been found by previous authors. That is, the growth rate of the instability actually increases with increasing Roberts number, which means that more efficient is the thermal mixing of the system, more unstable is the system. So, and the second is that even the twist of the tubular structures which I showed you also increases with increasing chi to eta ratio. So this is an interesting result, which means that suppose I have these magnetic field lines here which are colored according to J dot B, And for two different cases of the Roberts number, one is a very high Roberts number, which means high thermal, high temperature conductivity, and other is a low Roberts number. You can clearly see that the flux tubes in the low Roberts number case are less twisted than in the high Roberts number case. So which may be favorable because the sun might have such conditions in the overshoot layer, and that might lead to formation of twisted flux tubes at the bottom. Now to look at the time evolution of this system, we define the mean fields, which are basically horizontal averages, since we have periodic boundary conditions in the horizontal direction. So the mean fields are defined as the horizontal averages, and they are only functions of the vertical coordinate. So for example, the total magnetic field is defined as B bar, this is the mean horizontally averaged field, plus a little b, which is the fluctuation, and similarly for the velocity. So this, the upper contour plot is a plot for By. Remember that we started with a non-zero strong By, and Bx and Bz were initially all zero. So you can see that initially this was a coherent layer, and then gradually with time this breaks up. So similarly here, this is the time evolution of Bx bar, which means that we actually generate a Bx from a zero, from initial 0 Bx, and this is how it evolves with time. And these are the URMS values of velocity and the magnetic field Bx square plus Bz square, which is generated from an initial 0 value. Yeah, so one of the objectives of defining the mean field is to ultimately have a mean field model for this kind of an instability. So basically to solve this mean field equation by modeling this EMF E bar in terms of alpha and eta. So we use the test field method, which is described in these two famous papers here. And there are these three steps for calculation of the alpha and eta from the equation for the little b. So here in the equation for little b, we replace the mean field on the right hand side by test fields. So test fields are 2 MHD watt, test charges are T electrostatic fields. So by doing that, we do that, and then we calculate the test EMF. Then we invert this algebraic equation, the linear system of this equation, to get our unknowns alpha and eta from it. But there are slight complications. One is that since my magnetic layer was thin compared to the size of the box, the turbulence is supposed to be inhomogeneous. So which means that alpha and eta should depend on Z strongly. So then this simple formalism where the mean EMF is proportional to the mean magnetic field and the mean current actually breaks down. And what we have to do is we have to write this whole thing in these multiplicative terms in form of convolutions, which are defined by this integral here. So these alpha and eta tensors are not simple scalars, not simple scalars anymore, but they are kind of Green's functions here, and of course they are functions of time. So in general, we can represent these alpha and eta by Fourier transforming them into these hatted quantities here, Fourier transforming them in terms of one of the spatial coordinates. But there is again another complication, that is the inhomogeneous turbulence that we have is valid only for the mean strong field that we put in initially in the system, which means that we really need to have these tags B bar on these hatted quantities here. So these tensors that we can calculate through a test field method are actually valid for the particular mean field, which means that maybe it is difficult to get a mean field model out of these alpha and eta, because this becomes a chicken egg problem. Which do you calculate first? If you want to calculate alpha, it depends on the mean field B bar. If you want to calculate B bar, it depends on the hatted quantities. So anyway, we still go ahead with this, and since we have defined our mean fields as horizontal averages, we can, without loss of generality, set Bz to 0 instead of a constant. And then we have 8 unknowns, 4 of alpha hats and 4 of eta hats, which are again tagged with the mean field B bar and the Fourier mode K of the B bar. So the value of alpha and eta actually depends on the scale of the turbulence which you want to probe. So we solve the test field equations for each K. I have all half integral as well as integral values which can fit into the box. And these are the test fields which we call the harmonic test fields, and they are either cos kz or sin kz. And then we determine these hatted quantities. And when we do that, we find that these alpha tensors and the eta tensors are actually smooth functions of K. But one of the surprising things is that I've been saying that these quantities are non-local. Now what do I mean by that? One of the examples is that if you calculate the pumping, the turbulent pumping gamma, which is basically the difference between the off-diagonal terms of alpha, then the sign of the pumping actually depends on the scale, which means that if you have By of scale smaller than 5 times the width of the magnetic layer, it is always pumped towards the layer, whereas those with higher scales are pumped away from the layer. So this is what it means by local. But now since we are using the test field method, there are 2 reasons why we should really check that the results we are getting are really correct or not. One is that this is a quasi-kinematic test field, which means that we are only solving the equation for little b and we are neglecting any velocity, any other velocity equations. And secondly, we have used harmonic test fields. Maybe there are other harmonics in terms of other derivatives, special derivatives of B, which might be interfering with such an expansion. So one of the easiest way of checking it is to reassemble the EMF that we obtained from this alpha hat and eta hat and add them up and then see whether this reconstructed EMF, which is denoted by an R superscript, is equal to this actual EMF that we get from the DNS. So that is what we do. So the left panels here, the top panel here is EX from the DNS and the lower panel is EY from the DNS, and the second panel is the same but which has been reconstructed using 16 Fourier modes in the system. And the last panel here shows the EMF, the reconstructed EMF one would get if I use only one mode, which is the lowest wave number that fits in the box. So visually these two seems quite reasonable, but we also have some quantitative results for skeptics, and which is that we have defined a chi-square, which is kind of an error between the actual EMF and the reconstructed EMF, which has been plotted as a function of k here, and the solid line is for the x component of the EMF, and the dashed one is the y component. And we see that after a while, this kind of stabilizes to a certain value, and even though we keep on adding more modes, it really does not help. And similarly, we have a correlation function of the 2 patterns, the EMF from the DNS and the reconstructed EMF. And we see that the correlation is really good. It goes to something like 0.9 or something for EX and a little lower for EY. So this is an important result from our study, which shows that the quasi-kinematic test field method, even though it has a lot of assumptions in it, that still works for this complicated problem here. And the next interesting result is what was found by Schmidt and proposed by Telen as well, that the alpha and the eta tensors are actually anti-quenched, which means that with the magnetic field, which is increasing along this axis, the alpha and eta tensors also increase. And this may have some possible observational implications when you consider the stellar, when you consider this dependence of cycle amplitudes on stellar cycle frequencies. And then next we also have studied the dependence of this instability on the rotational inclination. So basically the angle between the rotation and the gravity. So it is quite obvious that this instability actually, the growth rate of the instability increases as we go towards the poles, because the vertical motions which are predominant thing in the magnetic buoyancy instability are suppressed because of the Coriolis force, which has a stronger influence as we move towards the equator. But a surprising thing is we get a non-zero EMF at the equator. So this is the generated field Vx, which is actually non-zero at the equator, and this is the corresponding EMF, which is non-zero at the equator. So if we are surprised, then I have another result about the case where we put omega equal to 0. So here can we predict the final helicity of the magnetic field? So the idea here is we have the same setup, except we have put omega to 0, and we have an initial velocity which varies like this, sine of kx plus ky plus kz, and we start with two different modes which are exactly same, but they differ in the sign and the sign of this kx here, and I have a different value of kx here. And in this case, we get a positive value of j dot v, and here we get a negative value of j dot v. And to represent them in a more consolidated fashion, so for these two pairs of modes, this basically corresponds to the velocity, the initial velocity. I get exactly equal and opposite kinetic helicity w dot u. Similarly for these two cases where kx is +8 and -8. And note that we started all runs with initial omega dot u equal to 0. So now you might think that suppose I add this mode and this mode and feed it into the system, then the initial helicity would be 0. Yeah, so this is a run where we started with such a thing where the initial velocity is a superposition of these two modes, and we actually got a mode which developed into a finite kinetic helicity, finite kinetic as well as magnetic helicity. So, but a similar thing has actually been observed in this paper which by Gellert, Digger and Hollerberg, which were discussed in the previous talk. So, with reference to the Taylor instability. So, the idea here is that there may be two modes in the system which might be either competing or aiding with each other, and at the end, the final mode that we have is actually helical rather than being non-helical. So we are actually in the process of still understanding what is exactly happening here, and we would be happy to know how many of you are really surprised at this result. So now I go over to the summary, where we see that this growth rate and twist increases with increasing Roberts number, and we have reconstructed the turbulent EMF, and we find that the quasi-kinematic test field method works for this problem at least. But the downside is that it's difficult to model alpha and eta as well, and use them in a mean field dynamo model. And then, since the alpha and eta are highly non-local, which means that the sign of the turbulent pumping velocity also depends on the scale of the magnetic field that we are talking about. And then this is this result about the anti-quenching, which means that the turbulent diffusivity in the magnetic layer actually increased to something like 50 to 100 times the molecular diffusivity that was there in the layer. This is exactly contrary to the quenching of diffusivity that we assume in strong field regions in the sun. And lastly, we have generation of kinetic helicity and alpha for omega is equal to 0, as well as at the equator for omega not equal to 0. So these are some of the questions we would be pondering on in the coming. Thank you. Thank you.
So we have time for a few questions. I've got first question. You produce turbulence in new instability. So before it was totally stable, no, without any velocity in the beginning.
Yes. Not without any velocity. Our initial equation has a velocity, but it's something like 10 raised to minus 6 times
So
the Mach number.
you've got some perturbation which increases.
Yeah, it's a perturbation. Does not have any meaning.
And you mentioned that in the beginning you've got some artificial cooling in order to keep equilibrium.
Yes.
Have you support this cooling during calculation?
Have I?
Have you support or continue this cooling during calculation?
No, the cooling. Initially we cool it, but later on, with the time evolution, the temperature actually of that magnetic layer increases, but it's always much cooler than the surroundings. That is because we obviously have viscous heating as well as diffusion in it.
Right, but without cooling, in continuation, it's another problem.
Oh no, if I, instead of having cooling, if I keep the entropy the same and decrease the density, then also this instability stays.
Again
But
artificial.
Yeah.
Thanks for the very nice talk. This sign dependence of the turbulent pumping on the size scale, that strikes me as a very intriguing result. And I was wondering if that, just as a wild guess, might actually be an explanation for the filamentary structure that we see in the sunspot penumbra.
Was that a comment?
Maybe you can comment on that, or if you have a picture how you might explain that it's the small scale structures that behave differently.
Yes, but actually we haven't thought of that. But maybe yes, we can.
This non-locality of the Green's function is very interesting. Do you think it's due to the fact that it had a layer in the first place, or to the non-linear nature of the instability? If you had a smooth layer, if you did the instability in a smoothly varying layer, but it was still a non-linearly driven instability, do you think you'd still get this non-local Green's function?
I think we would, yes.
So you think it's due to the non-linearity?
I think we would, but it's a different, but they won't be same as these. So the variations of alpha and eta that I showed with K, they may not be the same. So
Sure, but it'd still be non-local.
But I think it still would be non-local.
And just to comment on the last question, I think most people think the structure is due to some kind of fluting instability, the size of the structure in a penumbra. But I don't think there's a very good theory for that. So if you have one, then
Any other questions? So if not, let's thank the speaker again for this interesting. Let's go to the last speaker of today. This week, now we have Marie-Farge, if I'm not mistaken, that's the real name, which she will be speaking about what wavelets can bring to study and match the flow.
If we don't make it here,
One second.
Okay, thank you very much for the invitation and happy birthday to Karl-Heinz. And though this is joint work with some Japanese colleagues from Nagoya University and also with Kai Schneider from Marseille. So, well, I kind of assume many people have heard about wavelets, many people have heard about turbulence, though my first paragraph is going to be running through very few things to get some background. And then I will tell you about this, show you result about this technique for extracting coherent fluctuation out of MHD turbulent flows. And if we have time, I will show how we expand that to directly compute in wavelet coefficient space the flows. Okay, though you know there are some differences between hydrodynamic turbulence and MHD turbulence, but they are not that major difference. Of course, when you look, okay, the two cases I'm showing here, they are homogeneous isotropic turbulence, either without Lorentz force or with. And, but here you see in hydrodynamic turbulence, you observe that fluctuation, the mean is zero everywhere here, because homogeneous isotropic, but these are only fluctuations. But just by watching the fluctuation, you see some organized structure that we call them coherent structure in the field, although this name is not well chosen. I would call them coherent fluctuations. And they look like vortex tubes. In the case of MHD turbulence, the vorticity fluctuation look more like vortex sheets. Okay? And the current field itself just show also some sheet-like structure. But they are all, again, fluctuation, but the coherent contribution to fluctuation have a slightly different kind of geometry. You all know that, we heard that a lot today, that you split the field between the mean and fluctuations. But here we are going to propose something new, which is you just look at fluctuation. Again, I repeat, I insist on that. In everything I'm going to present here, the mean is zero. We are going now to propose something new, which is to split the fluctuation themselves between coherent contribution and incoherent contribution. Well, and I remind you, this is the key problem with turbulence, that, okay, at least I myself from hydrodynamic turbulence background, and in hydrodynamic turbulence there is evidence that we have no scale separation. And when you have no scale separation, you have this big problem with the nonlinear term of Navier-Stokes equation, and because of that you get this Reynolds stress and all the problem of closure of the equation. Okay, so I assume it's going to be more or less the same for MHD turbulence, and as a result, it has to do with trying to go around this problem that we introduce this coherent fluctuation versus incoherent fluctations. And actually, we got inspiration from this beautiful quotation I want to share with you, which is an old one by Hugh Dryden, 1948. He's the one who was founded NACA, which then became NASA, a really important person. And he explained that at the International Conference of Mechanics, 1938, Tolmien and Prandtl suggested that turbulent fluctuation might consist of two components, a diffusive and a non-diffusive. Their idea that fluctuations include both random and non-random elements are correct, but as yet there is no known procedure for separating them. So we were in 1948, and the kind of batch we are doing today is the fact that now we are 2011, and we have slightly new technical tools at hand, and one of them is the wavelet transform. And I pretend, and I'm going to try to demonstrate that to you, that using the wavelet representation, now we will have some technicalities to do the following. We take turbulent fluctuation and we split between non-random contribution and random contribution. The non-random, we call them coherent structure or coherent fluctuation, and the other one is incoherent noise. You will see both are multi-scale. That will be the difficulty here. I already tell you why not reason. They are not large scale, small scale. They are multi-scale both, but they have different statistical behavior, different correlation, and different probability distribution. This is the key idea behind the scene. And out of that, we are going to propose some technique to extract coherent fluctuation out of the turbulent fluctuations themselves. Then the consequence of that is also that the dynamics can be split, the turbulent dynamics can be split into some chaotic non-diffusive contribution and some stochastic diffusive contribution. And of course the idea will be that to kind of cancel that, either then model their effect on the other one by some kind of model, but even if we have time I will demonstrate that even if you do well the split, you even don't need to have any modeling. I mean, a very general program in which I'm working is the following. Try not to throw the baby with the water, and if you do that, you don't need modeling. It's of course a very kind of provocative and long-range program, and not throwing the baby means keep everything nonlinear. Everything which contributes to the inviscid nonlinear dynamic, don't throw it away. If you throw it away, you will have a modeling problem. Okay, and if you throw it away, okay, though if you don't throw it away, then this you can cancel that this term. Okay, these are in many papers. You can just wonder if you want to know more. Okay, so now here is the problem: how to define coherent fluctuations. So in the field of let's say again hydrodynamic turbulence, we have been. Now it has about 20 years that people recognize that what we call coherent structure is important. But of course no one managed to agree about a clear-cut definition about what are coherent structures. And as a result, if you don't have a clear-cut definition how to extract them, and because extracting them means like having a template and then I take them out. Though finally, because I mean, we got this idea that, okay, if there is no template, if we don't have a clear-cut a kind of shape for coherent fluctuation or something like that, then let's take the problem the way around. Instead of trying to define what coherent fluctuation are, we just define what they are not. Okay? If you agree on a minimum definition, like the coherent fluctuation are not noise, they are different from noise, they are not random. They are due to the nonlinear dynamics of the flow. They are not random, although they are highly fluctuating, but they are not random. Then, if they are not noise, then the problem of extracting coherent fluctuation or coherent structure become a problem of denoising. And here you have to believe me, we have techniques for denoising, and wavelets has played a key role there. And though we are going to base our technique on the wavelet representation to do denoising. Though now we have succeeded that we don't need to have hypothesis on the structure themselves, coherent structure, current fluctuation. Now we need an hypothesis on the noise. The noise we want to get rid of in order to recover the current structure. The simplest, okay, you know there is a method in science which is since Occam's razor principle, you start with the simplest hypothesis. So the simplest for denoising is to assume that the noise is Gaussian, it's additive, Gaussian and white. So we get started on this hypothesis, we try it, and if it doesn't work, we make it more complicated. So that's the research program I'm going to show you. Well, very briefly, I'm going to run through wavelets, but you know, wavelets, what is new with wavelets is that they are localized functions, I mean just a wave packet, but the main idea, it's not the fact that they are localized, the main idea is the fact that you are going to generate your basis, the basis of function used for the analysis is going to be made by translation and dilation, which is a very different operation than from what you have with window Fourier transform, which is translation and modulation. We are not going to modulate, we are going to dilate. And as a result, the set of dilated and translated wavelets, I'll give you an example here, will correspond to filters in K-space of different boundaries. You see, they have different boundaries, and what is constant is delta K over K. So it's different from a Fourier window Fourier filtering. You have to keep that in mind clearly. And the idea behind the scene, I'm not going to detail that, but it's just optimal in front of the uncertainty principle. This is the idea. We do the best. And also in terms of sampling, you are always at the limit of liquids at each scale. That's a key idea behind wavelets. As you know, wavelets, then you can construct orthogonal wavelet bases. And what I'm going to work with is three-dimensional orthogonal wavelet basis, because I'm going to show you a three-dimensional simulation. I don't get into detail, but for people who know wavelets, we have chosen this wavelet, which is Kaufman 12 wavelet. Okay, here is just an illustration on an academic example about the method for denoising using wavelets. So let's take a kind of nasty signal, which has some cusp, I mean, it's continuous, but it's non-regular. There are some, singularities, like this kind of different kind of cusp. Okay? Then you put you put a noise, quite strong. You add a white noise. So then you get that. So now I want to denoise this to recover the best recovery I can make out of this noisy signal. So then the techniques, and it's based on some mathematical work proposed by Dono and Johnson in '94, and we have, I will explain then what is in this paper. Okay, so based on their work, the technique proposed is you take this, your noisy signal, you go to wavelet coefficient space, so you get this wavelet coefficient, and then you're going to retain, to reconstruct your denoise signal, only the coefficient whose modulus is twice the variance of the noise multiplied by the logarithm of the number of samples, just the number of points, samples you have. Okay? And if you do that, you recover that. And you reconstruct, you inverse transform. And as you see, of course it's not perfect, but the errors are very local, where you have discontinuities, you have jumps here, and the rest is quite smooth, and you don't have all the wiggles kind you will have if you were using other denoising technique based on Fourier representation. Okay, that's the idea. In the case of turbulence, you see, the way I present the algorithm, I said we take twice the variance of the noise. The problem now, when we are going to deal with a turbulent signal or a turbulent field, we want to denoise it, but we don't know the variance of the noise. We have the assumption it's additive, Gaussian, white, but we need to know the variance. Though we have developed a technique, which is in this paper, where the idea is the following. You make a small iterative procedure, where here you start with the variance of the overall signal, which is an overestimating of the variance of the noise. You take the variance of everything. Okay? And then you just remain in wavelet coefficient space, because you have it's an isometry between physical space and wavelet space, and within very, very few loops, you just find out the best threshold, which means you first put this threshold, and then you look at the weak wavelet coefficient, the one whose modulus is below this threshold. That gives you a new variance, which is going to be weaker, and you redo that, a weaker variance, and at the moment it will converge. The variance will be the same, and that's what will give you the denoising without even knowing the variance of the noise. And in this paper we prove, there are some mathematical proof of that if you start with only noise in one iteration, you say it's only noise, and if you have a signal which has no noise, you need n iteration. Though it will always converge anyway, but in a very much more. Okay? Here we have in the wavelet coefficient. I'm going to skip that because it's maybe a little bit technical for you, but there is this idea that we are orthogonal. You start, okay, all what I'm going to present, we are going to work with three-dimensional data set, because it's a three-dimensional like vorticity field. We go to wavelet coefficient space, you still have the same n cubed number of coefficients, because it's an orthogonal transform, and then it's in this wavelet coefficient representation that we are going to select. The red will be the one larger than the threshold, the blue the one smaller than the threshold. And here it is actually the wavelet representation. Here you have the large scale, smaller, smaller, and smaller scale. But I don't detail too much. And you have direction. We can also separate direction. We separate scale, direction, and position. And you have different positions. Each coefficient tells you I am here in space. Okay, this is a very powerful representation, but I don't have enough time to detail everything we can do. Actually, recently we have introduced, and we have a paper about that, also, well, I should advertise for this paper, but I have no time to explain the content, about scale-wise helicity. I mean, we go to wavelet coefficient space and we look at helicity, but at different scale, at different positions, and different angle. Like, you may be interested by that kind of work. Okay, so now, application to turbulence. We are going to do a numerical simulation, and we are going then to use our algorithm to do this denoising, extraction of the coherent structure. Okay, these are the equations. You know very well them. I skip that. The code itself is a very standard one, d-alias, pseudospectral, with force order, Runge-Kutta. We have a random forcing in the large scale, and okay, our magnetic front number is 1, and we get into a quasi-stationary state. This actually is based on the work people who made the simulation are these Japanese colleagues. So our role is mostly to do the extraction then. These are the parameters of the simulation. It's 512 cube, and here are the results. Okay, so out of the simulation we got that, the vorticity, the modulus of the vorticity, and here the modulus of the current. And this is what we are going to split into coherent and incoherent contribution. And we are going to do it independently. We are going to do the extraction for the vorticity and for the current density independently. And here are the results. That's the total and the coherent. If you look for vorticity, if you look well, they look the same. The J looks the same, current look also the same. You have like this tiny tube or sheet piece like that, you see them here. If you watch carefully, they look very much the same. And in terms of compression, you find out that only 2.3% of the total number of 512 cube, coefficient, reconstruct all the coherent contribution, which contain 93% of the kinetic entropy and 99.8% of the kinetic energy. So with only 3% of coefficient, you get about all kinetic energy. And you will see for current density, it's even better, because with 3.2% of coefficient, we get about 94% of magnetic entropy and 99.9% of magnetic energy. So very few coefficients are enough for that. And the left, the coefficient we are going to discard, there are very many. And you see by eye, they are not organized. And more than that, in the color scale, we have renormalized it. If we have kept the same color scale like this one, you will see just white. You will not see anything. The fluctuations are too small. So we are just renormalizing by a factor 3. And you see something which is not very organized. And here, they're actually made out of 96.8 coefficient, which contain only 0.1% of the kinetic energy. Same for the magnetic, for the current here. They contain only 0.06% of the magnetic energy. So you see the compression is very efficient. If you look at PDF, green and red superpose, that means we get for both vorticity and current density exactly the PDF with only this 3% of the coefficient. And the remaining, the leftover, the noise, is this blue, which variance is very reduced. If you look at the spectrum, we get the Hiroshnikov-Kreshnan spectrum here. And the total and coherent superpose perfectly. It's obvious because you retain 99.8 or 9% of the energy. So the two spectra are going to do the same. But the more interesting things to remark is the fact that the incoherent contribution to the energy is going to be at this K+2 spectrum, which corresponds to equipartition of energy. So because we are in 3D, so if you are in 3D, you integrate on shell, and therefore K squared d theta. And equipartition of energy will give you a K square scaling. What does it mean? It means that we have retained all energy on the coherent part, and the very, very tiny leftover, they are actually equipartition. There is this idea behind the scene that it's a kind of thermal noise, what we hope. And then if you look now at the nonlinear transfer, you just look into you just do one time step to compute the nonlinear term, and I don't detail too much, but you compute the energy flux and then you plot it, and you see that these are the K-space, and these are your energy flux. In green and in red, okay, now you have kind of a lot of interaction, because you have the incoherent, coherent interaction, You have all these interaction terms. I'm not going to detail them. The main message you see on that is the fact that the total and the coherent CCC, where is the CCC? Yes, the CCC, they just superpose. All the inertial range perfectly superpose. Only in the dissipative range, you begin to have a very tiny contribution for where incoherent contribution play a role. So this is a message. With this extraction, we have managed to get all the nonlinear dynamics with only the coherent contribution, because it's the CCC interaction which dominate. Then we have also analysis made based on wavelets, where now we can have a scale-dependent flatness, because now we are in wavelet creation space and we have a different scale. And though if you look at the scale-dependent flatness, so this is your scale here, and this is your flatness. If you look at the total and the coherent, they superpose, and the incoherent is about 3. Though that kind of confirms the Gaussianity assumption we were having for the noise. And this is for the velocity, and for the magnetic field it's even more. I mean, what does it mean? It means that the fact that flatness increase when you go to small scale means it's highly intermittent. And here the maximum is going to be 150. But if you look at the magnetic field, it's even more intermittent. We get up to about 250. Though through this analysis, we show that we have extract the coherent contribution to the magnetic field, but it's also more intermittent than what it was for the velocity field. And that concerns some remark already made by Cho, which said that the magnetic field is more intermittent than velocity. Then, now what we do, and I think you will appreciate that, now we compare the split made in wavelets between coherent and incoherent, whatever the scale. I recall, I go backward here just to make sure you have understood. The coherent in red and the incoherent in blue are all range of scale. It's not large scale versus small scale. It's not low wave number versus low wave number, high wave number. You see, it's multi-scale, both. Just have different correlation. This one is decorrelated, and this one has this long-range correlation k minus 3/2. Okay, so now we are going to compare with Fourier. Oh, sorry, I'll go back once more. Now we are going to compare where we do a cut like here, large scale on one side, small scale on the other side. Fourier cut. And we will do a cut which retains the same amount of energy, to be fair for Fourier. Okay, though here are the comparison. Though for the same compression rate, for the same, I say energy, no, it's compression rate. For the same compression rate, you have either coherent, incoherent, for the vorticity, the same for the current density. So you see the incoherent, you see very little. Now if you do with the same compression rate, the same number of modes retained, large scale versus small scale, it's not, you cannot say it's incoherent here, it's very organized. That's for the vorticity modulus and also for the current density. And we did exactly the same, the visualization is made with the same scale. What does it mean? It means that when you do the split between large scale and small scale, a given structure, I just picked that by chance, you can pick any other one, has a contribution in the large scale and a contribution in the small scale. And this contribution is organized. What does it mean? It means that this small scale contribution is going to contribute to the nonlinear dynamics. That's, if you throw that, you throw the baby. That's part of what we try to say. And though if you throw that, it's not the issue. This is not going to be active anymore. I mean, there is no nonlinearity. There is really this idea, beware not to throw something which would contribute to the nonlinear dynamics, because then you will have this modeling problem, which is nearly impossible to solve. Okay, and then when you look at the PDF, you find out, believe me, when it's green, red and green superposed for this is the wavelet approach, and here is blue, the incoherent. In the case of Fourier, this is a difficulty with Fourier, because this is the green, the total, and, well, you don't see well, but the red is about the same. Okay, that you have the, no, well, okay, you have the green here, you have the red, so you have already lost some extrema that you have not lost here. But, yeah, when I say the same, sorry, I made a mistake, the large scale and small scale, they have about the same variance. You have not kind of reduced the fluctuation as we have done here. And it's even the same also for the current density. This is the red for the large scale and the blue for the small scale. So you have a problem. And also, for instance, here the contribution to magnetic energy is non-Gaussian. Then you will have a modeling problem. It's not going to be easy to do, while here we are Gaussian. Okay, so I go on. How much time I have left with? 3 minutes. Okay, I'm going to run a little bit. Okay, so this is okay. I want to insist on the fact that we are proposing a different viewpoint to understand, to describe turbulence. Our viewpoint is that here is the spectrum. We have decided that the nonlinear dynamics works all over the range of scale. Even at very small scale that normally you assume is dominated by dissipation, there is still some nonlinear activity. Of course, because of intermittency, the spatial support is going to be small, but it's there. If you cut them, you will kill some part of nonlinear dynamics. Of course, because the spectrum decay, okay, we have decided that the incoherent contribution is equipartition of energy, though I put it on purpose here flat. So of course, in the very small scale, dissipation will dominate, but you still have nonlinear activity there. Tiny on the small support, but if you kill that, you will kill also some of the will happen in the future, a kind of butterfly effect because of inverse cascade. They will react to the. You should also remember that when we do simulation, there is a problem. Because when we do numerical simulation, we compute one realization at a time. But we have the bad habit that our modeling is based on ensemble average. All the theory of turbulence is based on ensemble average. So when we do a simulation and you have to model the effect of the small scale onto the large scale, you don't do it statistically, you do it in this flow realization. And that's where is the difficulty. That's where there is a lot of misunderstanding, I think. Okay, then if you look in physical space, the view we have of is when you have, okay, everything is fluctuating. Though we are talking only about fluctuation. The mean is 0. You have a lot of fluctuation. And then you see this kind of organized fluctuation. They still have a lot of nonlinear dynamics, like this kind of vortex interaction. And when they do this nonlinear dynamics, the model we have in mind, they emit a background noise. So this kind of incoherent contribution is more a background noise which is proportional to the level of turbulence. It's very turbulent, you will have a lot of this background noise. And this finally will dissipate by viscous effect, but in fact, we should throw it away right away because this is actually turbulent dissipation. It's not going to harm, it's not going to work and bring more nonlinearity if you have managed to make sure that it's incoherent, not organized. This is the idea. But the best way to represent all that is in fact to stay in wavelet coefficient space. So this is wavelet coefficient space. You have the position here and you have the scale here. And what does the nonlinear dynamics do? You know, they bring energy like nonlinear cascade to small scale, but it's not homogeneous in space. Now I'm talking for one flow realization. Of course, if I superpose 1,000 flow realization, on average, I'm going to have an interface, which is actually called the Kolmogorov scale, where dissipation will be dominant below that, and nonlinearity higher here. But when you compute a flow, it's one realization at a time, though it's highly variable in space. And so you need to have a method which just track where are the active nonlinear contribution. Though I put it in red, nonlinear contribution. And here I'm just making 1 minute to announce the method for simulating, for computing turbulent flows, MHD or hydro, in wavelet coefficient space. The technique is the following, that you extract the coherent contribution, what I've already shown you, the coherent fluctuation. But since you want to compute the next time step, and there is all the nonlinear, either Navier-Stokes or MHD dynamics, you have to be ready for the structure to move in space, but also to generate smaller scale. Though you add what we call a safety zone, you just add the neighbor wavelet coefficient in space and scale, and in 3D also in direction. And then this will be your computational basis. Then you integrate one time step, then you filter again, like prune the tree, add the neighbors, one more time step, prune the tree, keep only the coherent contribution. That's the method. And in the rest of my talk, but I'm going to go very run it. Now I will demonstrate it for MHD. These are the... Okay, what can I demonstrate? I can demonstrate that this is DNS without, not made in wavelets, and the green is made in wavelets. We have the same evolution for energy different thing. But we actually in this, which is a paper, we compare different way of doing our safety zone. But you see that we can get the flatness of vorticity right, the flatness of current density right, and with only 11% of the modes, including the safety zone, we keep also the skewness of velocity gradient okay. And if we were doing it in Fourier, we will not have the flatness of velocity gradient okay because we are destroying the PDF. And these are the conclusions. Though with only 3.2% of the mode, you see we have extracted the current contribution. Why we were having this 11% at the end is because we need to add the neighbor. And adding the neighbor in 3 dimensions costs us a lot of extra coefficient. Okay, so the technique is called, well, when we do it for hydrodynamic, we call it coherent vorticity simulation. And though we try a new name for when it's MHD, coherent vorticity and current simulation, because we do it also for the current field. Thank you.
Let's thank the speaker. Any questions?
Extremely surprising and convincing presentation. Do you have comments regarding inhomogeneous applications, applications to inhomogeneous systems, for example, systems with stratification, density stratification?
Okay, this is a good question. I mean, to me, density stratification, to me, it's anisotropic rather than inhomogeneous.
Oh, yeah.
Though, I mean, I first answer to the first question, which is inhomogeneity. As soon as it's inhomogeneous, it's much, much better for wavelets. We pick the homogeneous case because it's a standard case, but it's worse for wavelets, because wavelets, since we have locality in the coefficients themselves, each coefficient traces where we are in space. It's perfect when you are inhomogeneous. I mean, this is really the method, because the problem with Fourier, you have to assume homogeneity. Well, but wavelets, you don't have to assume homogeneity. And it's on purpose, just for comparison purpose, that we took the homogeneous case as the comparison, but it's the worst case for wavelets. So if we made it for homogeneous, then we will be much better for homogeneous. Then when it's anisotropic, of course anisotropic too we can, because we have the angle, we have also the direction involved. And the new paper I just very briefly mentioned, that's the very nice thing when you're in wavelet coefficient space. You can also look at things, anything you want, like helicity or other quantity, also in direction. And well, when you work with orthogonal wavelets, the directionality of the wavelets is not very, very good, because you have, okay, I just showed you in 2D, you have just diagonal, vertical, horizontal, 3 directions. It's better than nothing. But if you want to be very selective in direction, then you have to go to continuous wavelet transform, and after, which requires some redundancy. So when we are in 3D, we have, I think, if I remember well, 7 directions. You see, and we have plenty of results of analysis made in direction, and we have plenty of tools like statistical tools, the one you like, flatness versus direction and things like that. Though we can, I think, this would region, it's an appropriate tool for that.
Nathan, please. In our laboratory experiment with convection, we've got very pronounced scale separation between large scale shears and small-scale turbulence, at least one order. Is it true that even in this situation, traditional picture is not so correct?
Well, my answer to that, if you're happy with just what you said, you don't need wavelets, go on, it's perfect. I mean, when you have scale separation, you don't have to face the problem we are addressing here. This method is made for problem where there is no scale separation. If you are lucky to have scale separation, do homogenization, do mixing lines, do all the classical methods which work beautifully.
We find simple in experiment. It's not
well, keep it. You are lucky.
We'll try.
You focus on coherence and denoising in space, but in geophysical and astrophysical flows, you also have coherence sometimes in time. Do you think you'd be able to use those things to help you increase the efficiency?
I really enjoy your question, because that's something actually. I mean, for me, what we should do, but of course, as you see, it's a long way to develop the whole program. Of course, the right we need to work in space-time. I mean, for turbulence, it's obvious. And even you have some memory effect, you have some, you need to have also to have the time correlation, which play a key role. So what we did on this, okay, just to answer you, I have to be a little bit tricky in the answer. In first approximation, and we already have made that, you can use wavelets in space-time as a tool. But I give you what we did long ago. What we did, we took 2D field, time evolution. You see, I've shown you the separation just in each time step like that. But we took a 2D field plus time. That means just a big data set, and we did the extraction at once. Just the same procedure, boom, and we were getting the same answer that if we do it like that. Though the techniques work, taking the space-time. If you want to be very, very picky, there is a bad news with wavelets. That the full theory is based on is based on group theory. That, as I said, the wavelet is constructed by translation and dilation. When you in 1D, it's affine group. When you generalize it to 2 and 3D and ND, it's Euclidean plus rotation, Euclidean group plus rotation. Alex Grossman, the father of wavelets, tried to generalize it to space-time. And then there are some obstructions. They didn't find the right group, because then you get into all these very tricky problems about light cone, Doppler effect, because now your wavelets also move in space-time, and it's a little bit tricky. Though you cannot do it as a theory very clean. It's still work in progress in the wavelet community. I'm just sad that very few people develop that. The truth is that it's kind of hanging, no one cares. But practically, if you just play, consider that there is no structure of time. You just say time and space is the same. Then the method, wavelet orthogonal techniques work in n dimensions. So you just take your space and time as just a larger data set and you go. I didn't mention that, but the algorithm is very fast. It's even faster for large data set than the fast Fourier transform, because the algorithm scales in n operation, n being your number of points. And you all know that because if you use JPEG 2000, you probably know that it's made in the wavelets. I mean, this is already applying this denoising technique for your apparatus, photo apparatus.
Okay, I only have one very wholly last question. I was impressed to see that you can discuss incoherent fluctuation from simulations. To me, it's very difficult to understand this. I only thought that only coherent oscillation can be produced in simulations. So I'm a bit worried what you see, you call incoherent, is just a numerical noise.
No, not at all. That's really a key point. That's really a key point. Everything we are developing here, I should have mentioned that a little bit more carefully. That was, actually, this is the slides, which mean what I want for this answer. All that is developed for the fully developed turbulence. If you are not fully developed, that means you are just having some nonlinear chaotic dynamics. You still don't have turbulence. Yeah, but when you have turbulence, you have mixing. And having mixing means there is a part of your degrees of freedom which has reached some kind of thermal equilibrium. And this is this incoherent noise. And I like this plot, because this plot is just dissipation versus Reynolds number. And you know that if you are just not very high Reynolds number, although this is a microscale Reynolds number, beware, okay, your turbulence is, to me, more nonlinear dynamics, chaotic dynamics. But then, and of course, this is the viscosity of the flow, which is taking care of dissipation. But then, after the mixing transition, then, as you know, this is a D'Alembert paradox, dissipation or drag is independent of the Reynolds number. What does it, though it's independent of the fluid viscosity. What does it mean? It means that dissipation is due to the nonlinear dynamics of the flow. And that's what is going to create this incoherent contribution. We are really facing this problem of the D'Alembert paradox. What is the nature? The viscous dissipation is going to zero when you go to Reynolds infinite. But turbulent dissipation becomes constant. And that's what is this incoherent energy? It has to do with this.
Okay, let's thank the speaker again for this very interesting talk. Let's continue the discussion outside, hopefully not